Hello everyone, myself Mr. Sunil Kumar Singh, graduated in mining engineering from BIT Sindri in 1994 and MTech from BHU Varanasi in 2000. I am presently working as Head of Department Mining Engineering at Bilaspur College of Polytechnic, Bilaspur. Now I am here to deliver a speech on spontaneous heating of coal or spontaneous combustion of coal. Some of the contents are introduction, mechanism of spontaneous combustion, theories related to spontaneous combustion, factors affecting spontaneous combustion of coal, a stage of spontaneous combustion, detection of spontaneous combustion, preventive measures against spontaneous combustion and references. Now comes to spontaneous combustion. What is spontaneous combustion? Spontaneous combustion is an oxidation reaction that occurs without an external heat source. It is automatically taking place for coal. The process changes the internal heat profile of the material, leading to rise in temperature, because the spontaneous combustion is oxidation process, or oxidation process is exothermic, and as it takes place continuously, the heat goes on increasing and naturally the temperature rises. This can eventually lead to open flame and burning of the material like coal or other carbonaceous material that may get oxidized during contact with air or oxygen. It is a slow process, it is a very slow process, it cannot occur instantly, and heat evolved is carried away by the air, particularly in surface mines or in underground mines. In surface mines, the natural air carries away the heat produced, and in underground mines, the ventilating air carries that heat produced during oxidation of coal. This process of self-heating of coal or other carbonaceous material, resulting eventually in its ignition, is spontaneous heating or auto oxidation or auto heating. Coal can interact with oxygen in the air at ambient temperature, liberating heat. If the heat is allowed to accumulate, the interaction rate increases and may ultimately lead to fire, that is spontaneous fire. If such heat is carried away by ventilating air, then the chances of spontaneous heating may be less and even impossible. In Indian coal mines, 80% of the coal fires occur due to spontaneous combustion, particularly in coal mines of BCCL, Bharat Coking Coal Limited, Dhanbad, where the coal is of very high quality that has great affinity towards oxygen, and they get oxidized and catches fire. The main reason is that the Indian coal seams are thicker and there is a tendency of coal to spontaneous heating during depulering operation, where there is considerable amount of loss of coal in the Gulf area and continuous oxidation results in its heating, spontaneous heating. Self heating of coal can occur in underground mines, underground coal mines, open cast coal mines, shallow deposits and outcrops, coal stockpiles during transportation, and at the site of waste from coal mines in which there is some amount of coal that get mixed with the waste and which on oxidation causes heating or fire. Now come to mechanism, how spontaneous heating takes place. The oxidation of coal, like all oxidation reaction, is exothermic in eccentric. The nature of the interaction between coal and oxygen at very low temperature is fully physical, means adsorption and changes into chemisorption form beginning from an ambient temperature. When coal is disclosed to air or exposed to air, it occupies oxygen at the disclosed or exposed surface. Some fraction of the exposed coal substance gains oxygen at a faster rate than others, and the oxidation outputs in the production of gases, mainly carbon monoxide, carbon dioxide, water vapor, along with the release of heat during the chemical reaction. The rate of oxygen consumption is extremely high during the first few days, particularly the first few hours, avoiding the exposure of fresh coal surfaces to the atmosphere. If then down very slowly, except causing problems unless produced heat is allowed to assemblage in the environment. Under certain conditions, the accumulation of fire cannot be combated, prevented, and with sufficient oxygen air supply process may reach higher stages. Actually, the heat produced during oxidation, if gets accumulated inside the coal, the rate of oxidation becomes higher, and the rate of oxidation becomes higher, the rate of heat produced and heat accumulation will also become higher, and finally, a stage is reached that the temperature due to high heat reaches the ignition point of the coal and fire takes place or fire occurs. This is spontaneous combustion. The coal oxygen water vapor complex made during the initial stage peroxy complexes breaks down about the temperature of 70 to 85 degrees centigrade, producing carbon monoxide, carbon dioxide and H2O molecules. The rate of chemical reaction and exothermally changes with the rise in temperature and radical changes takes place, beginning at about 100 degrees centigrade, measured due to loss of moisture. This process leads with the rise in temperature, producing more stable coal oxygen complex until the critical temperature is achieved. The ignition temperature of bituminous coal is about 160 to 170 degrees centigrade, and that of anthracite coal it is 185 degree centigrade. Once the coal achieves its ignition point, the air supply to it will only increase the combustion, and an interesting matter is that the very high rank coal and very low rank coal goes under spontaneous combustion, because the high rank coal has banded constituents on its surface, which is very affinity to oxidize and causing spontaneous oxidation, whereas in very low coal, low grade coal, the presence of higher volatile matter gives rise to oxidation and causing spontaneous combustion of the coal. The anthracite rarely goes under spontaneous combustion, as it does not contain such type of volatile matter or banded constituents like biturene, clarine, diurene, fusane. Now come to the theory of spontaneous combustion. Some major theories of spontaneous combustion. This is the coal oxygen complex theory. This is given by Reid and Wheeler. The coal oxygen complex theory is the theory that depicts about the composition of coal that contains carbon, methane, oxygen and hydrogen. Such coal, when comes in contact with oxidation, they form oxides of carbon with water vapor and heat. Such heat, if dissipated, does not cause further oxidation and the chances of spontaneous combustion becomes less. But if anyhow such heat gets accumulated in the coal, it accelerates the rate of oxidation and hence its temperature goes on increasing. Ultimately, it reaches to the critical temperature of the air of the coal and finally, coal catches fire. Now, come to pyrite theory. Pyrite means chalcopyrite means copper sulphide. It means the presence of sulphur in coal also accelerates the rate of oxidation, because sulphur as well as carbon gets readily oxidized with oxygen, and the combined oxygen process is exothermic and gives rise to higher temperature. Now, bacterium theory. Some bacteria also causes the oxidation of coal and hence spontaneous combustion may take place. Phenol theory. Some aromatic compound or hydrocarbon presence in coal also gives rise to oxidation and finally catches fire. Electrochemical theory means the electrochemical process of oxidation to give rise to its temperature and ultimately ignition of coal. This is the coal oxygen complex theory. The establishment of peroxyl, radical and hydroperoxide is commonly to be conceived to the mechanism by which oxygen and moisture are initially incorporated into organic matrix. These species may rearrange, react or decompose to form wide range of oxygen functionally in the gaseous product. The following factors favors the oxidation process: type of coal, temperature, moisture. At ordinary atmospheric temperature, freshly exposed coal has affinity for oxygen of the air in contact with it, but the temperature increases, the rate of oxidation also increases. The oxygen is absorbed by coal on its surface by purely physical process, which however rapidly gives place to a chemical chain reaction resulting in oxidation of certain constituents of coal, and this oxidation process gives rise to temperature of coal and consequently accelerating the rate of oxidation, and this rate of oxidation gives higher temperature, which results in ignition of coal. Like all other oxidation reactions, the interaction of oxygen with coal is an exothermic with production of a small quantity of heat. The oxygen absorption reaction is considered to take place as the following: coal plus oxygen. Coal plus O2 complex is oxidized coal plus carbon monoxide, carbon dioxide, water and heat. Here water means water vapor. The heat from oxidation normally varies from 2 to 4 calorie per milliliter of O2 absorbed at NTP. It means higher absorption of O2 results in higher production of heat. NTP means here natural temperature and pressure. A rise in temperature of coal in consequence takes place, which has the effect of increasing further the rate of absorption of oxygen and production of heat. Higher heat, higher absorption and higher production of heat. The coal oxygen complex theory, the heat generated if not dissipated by radiation or conduction or both at a rate faster than it is produced, a further rise of temperature of coal takes place, which accelerates further the rate of oxygen absorption and production of heat until finally the ignition point of coal is reached. The ignition temperature of bituminous coal is nearly 160 to 170 degree centigrade and of anthracite coal it is nearly 185 degree centigrade. Here bituminous coal is of two types, coking coal and non-coking coal. Coking coal is highly susceptible for oxidation and non-coking coal of very low rank coal, very low grade coal is more susceptible for oxidation because of presence of higher content of volatile matter. Volatile matter includes the aromatic compound, which is highly inflammable, and hence they undergo oxidation and gives rise to heat and as well as its temperature. The mechanism of reaction between O2 and coal is quite complex. The reaction occur in the following 4 steps. First stage, formation of coal oxygen complex and heat generation. The second step, decomposition of these complex yielding of carbon dioxide and H2O molecules and formation of more sensible groups, carboxyl group, carbonyl group and phenolic group and heat generation. Third step, decomposition of these groups to at temperature greater than 100 degree centigrade, production of carbon monoxide, carbon dioxide, hydrogen, HO molecule and high degree of hydrocarbon, ethane, ethylene, propylene and heat generation. Fourth stage is decomposition of aliphatic structure, saturated and unsaturated hydrocarbon, production of carbon monoxide, carbon dioxide and water. Pyrite theory. Pyrite theory, pure pyrite, pyrosulfide of iron contains 46.37% of iron and 53.33% of sulfur and also reacts with oxygen of air at room temperature, emancipating heat and responsible for spontaneous combustion, because the sulfur has affinity towards oxidation and forming sulfur dioxide and gives heat, which ultimately responsible for increasing temperature of coal. Heating of coal could be caused by iron pyrites present in finely powdered and dispersed stage in the presence of moisture. It has been established that pyrite present in coal might assist the oxidation of its carbonaceous content by breaking down coal into smaller fragments and exposing large surface area to the air, as well as by elevating the temperature due to heat liberated from its own oxidation. The reaction of iron pyrites with oxygen and moisture gives products of larger volume than the original pyride, hence opening more pore area of exposure for oxygen, and which is a exothermic reaction, that is given 2 FeS2 plus 7O2 plus 16H2O. Products are 2H2SO4 plus 2 FeSO4, 7H2O plus 316 into 2 kilocalorie. This is large amount of heat which causes higher rise in temperature of coal. It also yields reaction product having greater volume than the actual pyrite, with the result that would break open any coal in which they are engulfed, and thus exposing a greater surface of coal to the air. Sulfonated coal have greater reactivity towards oxygen, especially in the presence of iron oxide. The bacterium theory. Bacteria also encourage self-ignition of coal due to bacterial action. Spontaneous heating observed in hay stalks and in wood are also known to be mainly due to the activity of bacteria. However, there is no conclusive proof of authenticate or dispose this theory. Hence, it is concluded that bacteria could cause only a slight heating which may not play any important role. Phenol theory. Many experiments have shown that phenol hydroxyls and polyphenols oxidize faster than other groups. If these are present in coal even in a small amount, it accelerates the rate of oxidation of coal, and finally, the spontaneous heating takes place. The electrochemical theory, it describes the auto oxidation of coal as oxidation reduction processes takes place in micro galvanic cells made by coal components. It is basically a theory that explains the system or process of oxidation at micro level. Some factors that affects spontaneous heating. The magnitude of spontaneous combustion depends on complex relationship of a range of internal means intrinsic and extrinsic factors. Intrinsic factors are nature of coal, coal characteristics and seam factors. Extrinsic factors are atmospheric conditions, geological conditions and mining conditions. Intrinsic factors, coal characteristics or seam factors, composition, rank and petrographic constituents of coal. Composition means contents of carbon, volatile matter, elements like carbon, hydrogen, oxygen, sulfur, nitrogen, etc. Rank means high rank, low rank. Petrographic constituents means it has some igneous intrusions or metamorphic or some sedimentary rocks. Friability, particle size and surface area of coal. Naturally, the size of particle is less, the chances of spontaneous heating is high. Higher surface area causes more chance of spontaneous heating. Moisture content. High moisture content reduces the rate of oxidation and hence the spontaneous heating rate also gets reduced. Presence of iron pyrites, it accelerates the rate of oxidation and the spontaneous heating rate becomes high. Bacteria has no considerable effect, and other minerals, if they are inflammable or chances of oxidation is more. extrinsic factors, means atmospheric factor, geological factor and mining conditions. First of all, climatic condition. Climatic condition means temperature, moisture, relative humidity, barometric pressure, oxygen concentration. Temperature is high, oxidation rate is high and chances of spontaneous heating is high naturally. Moisture, relative humidity, if they are high, the chances of oxidation is less and spontaneous heating also less. Barometric pressure, at higher pressure the oxidation is more and probability of spontaneous heating is also high. Naturally, oxygen concentration should be high to oxidize coal and this causes this more chances of spontaneous heating. Some geological factors, coal seams and surrounding strata condition. If coal seam of higher rank and surrounding strata condition also have carbonaceous matter, then the chances of spontaneous heating is more. Seam thickness, thicker seam has more chances of spontaneous heating as compared to thin seams. Seam gradient is not so much considerable because it is not directly related with spontaneous heating or oxidation of coal. Caving characteristics, if roof is caveable, it contains some fragments of coal which goes on oxidation and chances of spontaneous heating is more. Faulting and other geological disturbances, near the fault the coal gets burnt and at that place there is more chances of oxidation and this causes spontaneous heating. Coal outburst means the release of gas from coal seam and which accelerates the rate of oxidation and spontaneous heating. Friability, friable coal has more chance of spontaneous heating as compared to solid coal. Depth of cover, if depth of cover is more, in underground mines there will be higher temperature and at higher temperature the rate of oxidation is high. That is why higher depth mines causes more chance of spontaneous heating as compared to shallow depth. Mining factors, mining method. Mining method includes rate of advance, pillar condition, roof condition, crushing, packing, presence of timber or other organic waste material in abandoned area or dump, leakage. If rate of advance is high, then there will be less coal inside the mines and less chance of oxidation. Pillar condition, if pillar is whitewashed, it cut off the oxygen and oxidation cannot take place. Roof condition, if roof is strong, then crushing of pillar cannot take place, and if crushing takes place, it provides a free surface for oxidation. If groove packing is proper, no more chance of oxidation and less spontaneous heating. Similarly, presence of timber or organic material gives higher rate of oxidation and causes more chances of spontaneous combustion. Leakage of air gives rise to spontaneous heating because the availability of oxygen is more for oxidation of coal. Multi-seam working causes losses of coal and losses of coal gives more chance of oxidation and spontaneous heating. Ward out area, if properly packed, no more chance of oxidation. Similarly, heat from machine should be dissipated by the ventilating air, otherwise it accelerates the rate of oxidation and spontaneous heating. Stowing reduces the chance of spontaneous heating because it directly cut off the contact of oxygen with coal. Ventilation system and air flow rate. If ventilation system is accessional, means from bottom to top movement of air, the chance of oxidation is less and spontaneous heating reduces. Ventilation pressure, if ventilation pressure is high, more quantity of air supplied to the mines and causes more oxidation. Method of stockpile and stockpile compaction. If stockpile is compacted properly, no more chance of oxidation, and if it is treated with water, the chances of oxidation or spontaneous heating gets reduced. This is the table that mining conditions influencing spontaneous combustion, also contains some parameters you can see. Now, a stage of spontaneous combustion. There are 3 stages: incubation period, indication period and open fire. Incubation period between the onset of first oxidation and the time point when one can detect by its senses. In a broader sense, it denotes the period between the beginning of coal extraction in a district or panel and the appearance of first sign of heating. During incubation period, one does not detect heating during one passes through mine working. The indication period. The end of incubation period is the beginning of indication period. It is marked by sweating and haze, which is caused by the warmed up air from a fire area cooling on coming in contact with the cooler coal, rock, metallic surfaces and depositing moisture. The indication period is often of very small duration, lasting sometimes only a few hours and end with the appearance of fire stink. Open fire. After the indication period, open fire with visible active combustion breaks out. In open fires, seams seldom burn with a bright flame, but they glow development bluish white clouds of smoke. Detection of combustion in early stage, it working may be detected by physical and chemical indication given by heating itself. There are essentially 3 classes of detection of spontaneous heating: early detection of physical symptoms through the human senses, conducting thermal survey using thermal devices, monitoring gas concentrations in return airway and sealed off areas and making composition analysis of the mine environment. Early detection, this is the oldest technique. Reliance has been placed on these indications in the past for early detection of spontaneous heating. Developmental heating in GOF is generally accompanied by the appearance of haze and sweating of the strata. GOF stink or fire stink, there is production of sound, smoke and fire. These physical symptoms of heating can be identified through human senses. GOF stink, first indication of heating that can be detected by the human senses is the characteristic odor of the GOF stink in the air coming from the suspected area. The tarry smell, just like a smell of coal tar, is termed GOF stink or fire stink, is considered as a sure warning to the initiation of spontaneous heating since the earliest times. In the initial stage of heating, the smell resembles of the petrol, but as heating progresses, it changes to kerosene and later to a tarry odor. A strong smell indicates that the heating has made sufficiently headway. This smell is caused by the distillation gases like saturated hydrocarbon and higher hydrocarbon produced during the oxidation phase. The characteristic smell normally found in a coal fire area one experienced can never be forgotten and cannot be missed. Haze. In the initial stage of heating, as the moisture released from coal come in contact with the cooler ventilating air and thereby condense, making haze like formation of cloud. The haze is visible little away from the seat of fire near the intake side of the ventilation. Typical signs are poor visibility of the mine environment in the vicinity of heating. This symptom is observed at an advanced stage after formation of haze caused due to condensation of water vapor released from coal due to spontaneous heating and formation of water droplets on the roof, walls, timbers, supports or any other cooler surface in its vicinity. At times, typical cracking sound from collapse of strata or due to crack formation in them may be heard behind the stopping or barrier, which could be indicative of advancement of fire. Sometimes increased activity and chirping of cockroaches and crickets, possibly caused by increase in temperature, may be considered a warning of the advancement of fire. A smoke in roadways may be observed above the ignition temperature of coal when fire has set in. Conditions: conductive thermal survey and second class of thermal survey, infrared scanner used in roadway side and thermocouples or thermistors also indicates the detection of spontaneous combustion inside the mines, but it has the demerits, that is thermal conductivity unlikely to withstand the mechanical stresses of active caving zone even when sheathed. Secondly, thermal conductivity of crushed rock is low, hence temperature even within a meter of an active center of heating may indicate known abnormal condition. Monitoring gas concentration in internal airway and calculation of Graham's ratio indicates the chances of fire. Sampling: we take samples of air in the downstream and calculate Graham's ratio and Young's ratio, which value indicates the condition of fire in the mines. Some fire indices that are used like Graham's ratio and Young's ratio. These are the ratio: Graham's ratio, Young's ratio, Willett's ratio, John and Trickett's ratio, oxides of carbon ratio. This is the numerical value of Graham's ratio that indicates the condition of fire, existence of fire in the mines. Prevention of spontaneous heating: this contains elimination of coal from area and control of ventilation to exclude oxygen entirely from the area or to supply sufficient flow of air to dissipate the heat efficiently as it is generated and before a critical temperature is reached. Several methods and strategy which can be adopted to prevent and control of spontaneous combustion in coal is mining layout. Proper mining method selected and design of general mine layout should be simple. Panel system of working should be adopted. Coal winning: the rate of production of coal should be high, so that no more fragments of coal to be present near the goaf area or at the face to avoid oxidation of coal. Ventilation and air leakage control: ventilation should be proper and air leakage should be minimum as far as possible. The ventilation layout should be a simple network of roadways and there should be no loss of oxygen or air inside the mines. Inhibitors and proper inspections of underground mines roadway where the suspected oxidation of coal or spontaneous combustion may take place should be detected at regular interval of time. And these are some references that has been used in this lecture. Thank you.